Okay, so today we're just going to go in detail through what we ended up talking about last lecture. All right, so we're going to talk here about the instantaneous center. Okay, so what is instantaneous center? I'm just going to give you a definition and we take it from there. Okay, so the instantaneous center I see is a point in space from which the motion of an object is only due to rotation. But that does not mean that the real motion of that object is rotation. Okay? But at that instant, from that point, the motion of, let's say, on that object will look like if it was in rotation. Okay? Okay, so for instance, what does that mean for the equation we have derived so far? So for example, if we have VA equals to what? VB plus omega cross S of A with respect to B. If it's only due to rotation, what does that mean? This term is zero, no? Okay. And if it's only due to rotation, and if we have this, I mean, this time will not be zero, but let's say, okay, let's say what happened, okay? We have this, don't put zero because maybe it was not good to write this one. Okay, so let's see here what happened with this one. We'll see what happened, okay? Put a question mark. Okay, so I'm going to put here the location of the instantaneous center is determined geometrically. Okay, so there's two classes example. First one, I'm going to give it to you, but I don't like to solve these problems using the instantaneous center because it's not required. But this is the classic problem, okay? Let's say you have a ladder, which is supported on, let's say, on a smooth surface. What's going to happen to the ladder if the surface is smooth? It's going to slide. So let's see if I can do another figure. So let's see, it's going to slide. Next time can be this one, no? Yep. Let me just do another one. And the next one could be, let's say, over here. Yeah, I completely made it up, okay? The angles, but. So what is the real motion of the ladder? The ladder is support of the wall and it's going to move in that way. So what type of motion is it having? So it's going to have translation. Plus rotation, no? Okay. However, so for example, let's say it's sliding down. So we have here, if we do the velocity of this point down and the velocity of this point going to the right. And we take from the origin of the velocities, I should not put ladder here, and we create a perpendicular. And we look at the intersection. At that instant in time, that point of intersection is called the antenna center, and you can study the motion of the ladder as is just due to rotation. Now, is that constant? Is that point constant in time, or is it going to change? So you see, at each time is going to change, no? Let's say if you take pictures, at each instant is going to change. So next one is going to be here. The antenna center will be located over here. And finally, this antenna center will be located over here. Okay, so really this antenna center does not have a physical meaning, like let's say the center of gravity or anything like, or the center of rotation, no? But if you want at each instant, depending on the velocities, you can find this location. So you can use it to solve this type of problem for the ladders, but you don't have to, okay? So personally, I don't use it, but you will see that many times solution on the textbook is gonna use it for this type of problems. Okay, so let's say if I look at this point, let's say this is, let's say I study the motion of point A over here. Okay, so from this figure over here, if I needed to study the motion of point A, the motion of point A will be equal to what? Omega, and here's what is strange, because you see that this antenna center is not even connected to the member, no? Okay. However, you agree that this bar can be moving with a rotational velocity. So if you study the motion of that object from the antenna center, you can say that the motion of point A would be what? Omega cross S of what? A with respect to this antenna center. But you see what is confusing over here is that this antenna center doesn't have to be on the object itself, no? It can be at a different location. Okay, so that's why for this type of problems, I don't like to use it. The other example that is being used, and in this case, we need it. So it's the antenna center. Is important when solving problems when a rigid body is rotating and not sliding. So what would be this type of problem? So for example, will be gears. Okay, let's say you can have whatever gears connected to each other this way, all right? Or planetary gears, like you have one here, okay? All right. Or running objects, which is the kind of the stuff that we did the other day. Okay, so for this type of problems, for these ones, you don't need this antenna center. For this one, there is no way around. You must use this antenna center. And you will see I will only use it for this type of problems, not for this one. It's going to be a little bit longer, but I think physically it has a lot more meaning. Okay, so here we go now to the stuff we did the other day. I'm just going to repeat it. And by repetition, you should get it. All right. So basically what happened? So let's consider let's say whatever, a ball that is rolling. So running is, the term running is important. Okay, and I think the other day, let's do it again. I did some figures. So let's say you watch a ball rolling at different times instants. Okay, I think I mentioned that the other day in this class. This is not differential equation. So basically here, you will look at the motion of one object. We take our camera, we take multiple shots, and then at one shot, we study what's happening to the motion of that rigid body, no? That's what we do in this class. So let's say here's the ball rolling, and we take different shots. So let's look at the motion of the center of the ball. So maybe let's call it A, okay? For A. Okay, so A basically is the CG, no? Center of gravity of the object. What type of motion is it having? We agree that the motion is translation, and I emphasize that upon only. So if I needed to plot the velocity, we could say this will be VA. And let's say I put on this one the acceleration, and this should be the acceleration, no? Yeah. So translation only, so that you will have what? VA, we only have one component on the X, correct? Okay, if we say this is X and Y. And you agree that we could say something similar about the acceleration. If we only have one component on the X direction. Okay, so next thing here, next point. The point of contact of the ball with the surface is, and what I'm going to write, instantaneous center. Why? Okay, if there is friction, that means that the ball is going to roll, no? If there is no friction, what's going to happen to the ball? It's just going to slide like a block, no? All right, so if there is friction, you agree that if I put this, and let's say the top of the marker is point A, is at that instant, it looks like it's going to rotate about this point, no? Yeah, so let's over here, this will be an instantaneous center. And let's call that point P. So this will be point P, point P. So let's say through an instantaneous center, and I'm going to put here point P. I don't know why I call it jolly point P, okay? But okay, so if this is an instantaneous center, what is the definition of instantaneous center? Is that the motion of that object will look like it's just due to what? Rotation. Okay. All right, so the velocity is going to be easy. So for the velocity, it's easy. And there is no problems at all. So let's say we want to calculate the velocity of point A from the instantaneous center. What would that be? VA equal to VP plus omega cross S of A with respect to P. Let's call that distance, whatever, R. Okay, so even without knowing that the instantaneous center is the point from which the motion of an object is just only due to rotation, what should be VP if the object is rolling and not sliding? Zero. Yeah. So you see that indicates that point P is already an instantaneous center because we only left with the rotational component, no? Okay. Okay, so this will give us what? VA will be equal to what? I JK 0, 0 omega. And what is the position of A with respect to P?
0 R
0 R 0. So if the math are correct, this should give you a component only in what direction? On the X direction or I component, the same thing, I or X. So do we get that? We only get the X component as expected. So here, no problem at all, no? Now comes the problem with the acceleration. So let's go back. The real motion of point A is translation only, and it only has a component on the A. Yes? Okay. So let me just redo a figure. That. See if I can do a better figure. So let's say now acceleration. That's fine. I'll go back to the screen. Acceleration. Okay, so here is a couple of ways to explain this, but I'm going to explain it the way I think is the less complicated, okay, to understand. So here we know acceleration of point A, only one x component, no, only on the y direction. That's the real thing. Okay, we know point P is an instantaneous center. Okay, so if we use the normal math and we say acceleration of point A from point P should be equal to what? A of P plus alpha cross S of A respect to P. And let's say we want to put them in here. I didn't put them in the previous figure. This is omega alpha, whatever. So we have the translational component, tangential component minus omega squared S of A with respect to P. Sorry. A with respect to P. I know it's not clear, but this is A with respect to P, okay? All right, so jump to one line and let's not neglect AP, okay, for now. Plus IJK of 0, 0, alpha. What is the position of A with respect to P?
So 0 R0.
0 R0 minus omega square 0 R0 if you want, okay? Or 0 R. So if we apply this, we get acceleration of A equal acceleration of P plus what?
Negative alpha.
Correct, negative alpha R on the X. But now, what do we get for the second term, which is the normal acceleration?
0 negative omega squared R.
0 minus omega squared. So if you want here, I'm going to put here acceleration of A 0. So we know the acceleration of A should only have one component on the X. So what is the problem that we're having here? We have one component on the X, one component on the Y. So in order to make it just to have a component on the X, what is the only solution we have?
Say AP equals to.
Is that correct? AP must cancel this term, no? Yes? Okay, so let's say here. Okay, I put the equation and then I write it down. So in this case, no, I write it down. So for acceleration of A to only have a component on the, whatever you want to call I or X direction, let me just say X direction. A sub P term must cancel the, oh, what did I change color? Sorry, the Y component due to the normal acceleration, which is minus omega square R. So what does that mean? the acceleration of A will be equal to 0 positive omega square r plus negative alpha r 0 plus 0 minus omega square r. So that what's going to happen, this term is going to cancel this term, and we have acceleration of A will only be equal to minus alpha r and 0. Let's see, does that make sense? If the motion of point A from point B is only due to rotation, it's only going to have one component. This component really, which one is the component that is, if you want, let me put it here. I'll give you the answer. The tangential, which one is the term that is tangential at the motion? Is the tangential acceleration, no? So if you look at it, this acceleration, which is really translation, is due to the tangential acceleration from point P. I know that's not easy to understand, but basically what you have is that basically, if you want to hear a quick summary, if you had this type of problem, and you go from the point of contact of the rigid body with the surface to the center of the object. So on a straight line, you have acceleration of I equal acceleration of P plus lambda cross S of A with respect to P minus omega square S of A with respect to P. What is something that you can do right away? You can say that these two terms will cancel each other, no? Okay, so let's do some not some examples, but let's practice a little bit this, okay, before we do real examples. So let's say here, let's say example or practice. Let's practice this, okay? So let's consider again another object that is rolling. This will be point A. This will be point B. And this is again point P, which is an instantaneous center. So if it's an instantaneous center, that means that dP is equal to 0, okay? I mean, you don't need to put that. All right, so here we're going to solve the problem two ways. Okay, I mean, it's the same way, but one will be two steps, the one will be one step. So the first step, that's the way you should do it for the first 2 weeks. Second step, once you are confident, you can do the second step, okay? In the one in one step. So let's say in this problem, I ask you, let's say this is R, and let's say this has some counterclockwise angular velocity and acceleration omega alpha. So I ask you here to find or to determine the acceleration at point B. Okay, so there's two ways to do this. The first way is the way I want you to do it the first couple of weeks. Then if you want, you can switch to the other one if you feel confident. So the first way, we're gonna do what? We're gonna go from point P to point A because we know what's happening. And then we can go from point A to point B. Okay? But once you are mastering this, what could you do? You could go directly from point to point B from point P. Skipping A. Okay? But you need to understand first what's happening, no? So that's what we're going to be doing now. So option 1. Recommended until you become confident. If you don't become confident, this is always going to work. Okay, so what can we do? We first can find the acceleration of point A. Do what? Acceleration of point A equal to what? Acceleration of P plus alpha cross S of A with respect to P minus omega squared S of A with respect to P.
We can go ahead and cancel. Wait.
Yeah, correct. So that was going to be my question. So now what can you do directly?
Cancel AP and.
You know these two terms are going to cancel because A sub A should only have one component here on the X, no? Yeah, that's what we just learned. So we can say here, acceleration of A will be equal again to the cross product I, J, K, 0, 0, alpha, 0, R, 0. And as before, nothing new. That's going to give us the acceleration of A is equal to what?
Negative alpha R.
Correct. Negative alpha R and the Y 0. That is what we just derived, okay, or explain. All right, so next, what can we do? Now that we know the acceleration of point A, we can calculate the acceleration of point B. So we can find AB will be equal to what? Acceleration of A plus alpha cross S of what? B with respect to A. Remember the one outside goes on top. Minus omega squared S of B with respect to A. What is the acceleration of point A?
What we just saw.
Negative alpha R.
Correct. Plus, we need to do the cross product again. I, J, K. 0, 0. What is the position of B with respect to A? So 0, 0 alpha, sorry. And what is the position of B with respect to A?
R 0, 0.
R 0, 0. Minus omega square of R 0, 0 if you want, okay? Or R 0. Or 0, 0 if you want, since you mentioned it. Okay, so this is going to give you what? Minus lambda R 0 plus what?
0 negative alpha.
0 positive lambda R.
7, yeah. Plus negative omega squared.
plus omega square r minus, sorry, and 0. So basically that's going to give at the end that the actuation of B will be equal to what? Negative alpha r minus omega square r alpha r. So you see, so if you do this process, there's no mystery. The only thing you need to recognize is this equation, no? All right, so now let's say continuous next page. All right, this time. All right, let me redo a figure again. I like figures, as you can see. Thing is a lot easier to understand. So this is point P, A, B, this is R. Okay, this time I'll be sketching some more stuff. So this time, in a couple of weeks, that you will be experts. What can you do? You can calculate, let's say, the actuation of point B from where? From point P directly. Can you do that? Yes, they're on the same solid, no? Same rigid body. So you could say A of B equal actuation of P plus alpha cross S of what? B with respect to P minus omega square S of B with respect to P. Okay, so here we go. So for now, don't think about anything. Let's just rewrite this equation. A of P plus, we do the first cross product, I, J, K, equal to what? 0, 0, alpha. What is the position of B with respect to P? Perfect, R0. And then the last term will be what? Minus omega square of R0. All right, so this will be equal to A sub P plus what?
Negative alpha R.
Negative alpha R. And then
Alpha R.
positive alpha R. And here I'm going to put plus minus omega square R minus omega square R. So if you look, okay, let's stop over here for 1 second. So you look at this for 1 second. What was A sub P doing over here? Yeah, but was canceling what?
Oh, the acceleration P is canceling the tangent.
The y component.
It's not a
Not
tangent.
tangent and normal.
But somebody mentioned the important thing. Canceling what? Canceling the y component. Correct? A sub P, so maybe it's a good thing to write it down here. A sub P cancels y component of minus omega squared S of A with respect to P. Yes? When you say the critical term out here. Okay, write it down. So now A sub P here is going to do what? It's going to do exactly the same thing. So what does that mean? This term is going to cancel what? Only the y component. It's not going to cancel the x component, no? Okay. So now if we do that, we're going to get A sub B equal to what? Minus alpha R minus omega squared R. And what are we going to get over here? Alpha R, which is a good thing. That is the same thing that we had before, no? Yeah. Let's say as previously. Okay, if you want me to plot it, generally I wait to plot it because I think it doesn't help too much. But if you think about it, the A sub P really is which component is the normal component going inside the motion, no? If I needed to plot it. All right. So I'm not expecting this to be 100% clear, but do you kind of follow or understand initially? Yeah. Now, a matter to be efficient at it is like doing the free shot, you need to practice, no? That's why you have the assignments, and we're going to practice a little bit together in class. So let's do a problem. And this is a classic problem. I think I saw it the other day. So the other day we're doing the 17, I think it was 1790 something, no? I think I saw it over there. So. I remember the problem, but I don't remember the data. So I mean, we could do it without data. That'll be a problem, but it's a bit faster when there's data. That's all I want to say. So why is this that way? Okay, so 17. Oh, that wasn't bad. So let's see. Oh, that's the one. Okay, 1744. That's this type of problem that I like. So no, but I want also the acceleration. So that's only half the step. So you see, you can have this type of problems as well. But this one is just velocities. So here you have instantaneous center. Basically, they will be saying about the same thing. Okay. So here you see the problem of the ladder. It's typical for this instantaneous center. Okay, this one is too long. This one is too long. Don't they have one which is I think I saw it the other day. So it must be somewhere here. Oh, here we go. This one, 1791. So copy 1791 and we do it together. Okay. So you see there is a 1 diameter disc is important. The term rolls is important. All right. And there is the bar D. A, B. Let's see, what do they give us? The ball is diameter. Let me just call it D equal to 1 meter. And the bar L will also be 1 meter. Determine the angular acceleration of the bar and the acceleration of point B. So alpha AB and A sub B. Oh, and they give us omega is equal to 4 radians per second. And alpha is equal to 10 radians second squared. Okay, so my figure is not as good, but that's basically the way it looks like, okay?
The diameter was 1 meter.
1 meter, yeah. Yeah, I should have just put the radius, but it's fine. Okay, are you done with the figure? Okay, so again, I like figures, so this is a problem statement. So again, this is something you have to do on the exams. This is the problem statement, correct? This is not the solution. No writing on top of it, okay, except this stuff. So in your solution, so let's say solution. What is the first thing you always need to do? Some type of free-body diagram, no? Or figure. So basically, I know it means to redo the same figure, but I don't care. It gives you time to think about it, to redo it. So we have here a point, let's call this one point A. So now that you are thinking about how to do it, what is the point of contact of the surface with the ball that is rolling? What is that point? P will be an instantaneous center, no? Yeah. Now, oh, let's not call it A because we already have an A. Can we just call it C? C. So now we have point A here and point B. Again, we have here omega and alpha. Now, okay, what can you say about point B?
So it's moving in the X direction.
The motion of point B is going to be restricted to the X direction, no? Yes? So let's say B, you can say here. So basically we can write it different ways. You could say what here, if you want, it doesn't matter which way we do it. You want to do it to the right or to the left, the velocity. Math will give us, okay, so let's just say, so we use right, so it would be VB, AB. So basically what I'm saying is that velocity of B here should only have one component on the X, and the acceleration of B should only have one component on the X, no? Okay, so that's part of the solution. And if you want here to simplify stuff, let's say R will be equal to what? Half the diameter, so let's say 0.5, no? And we know the length of this bar here is 1 meter, so L equal 1. What would be this angle over here? I don't know if we need it, but I don't know if we need it, but all right. If we need it, we go back, okay? All right, so we'll come over here. All right, so don't worry about it for now. So the idea is what? To start from one point where you know everything, no? The velocity and everything. So do we know the velocity of point P? 0. So we can start from point P, no? So again, we can go from point P, which I know we need to make it to point A. So you want to go straight or you want to go through point C? Straight? Well, can go straight, okay? I'd rather go straight, okay? That way we finish earlier. I mean, at least we finish for sure. But If you are not confident, what should be the way? You go first through point C, no? Okay, so we could write over here, but let's first do the velocities. So we can have velocity of A should be equal to what? Velocity of P plus, now be careful a little bit because I'm going to add one thing. This is omega of what? This is the angular velocity and the angular acceleration of what? Of the disk, no? That they call. So I'm just going to put an omega sub d, okay? Just to make sure it's the disk. Cross what? S of A P. So for the velocity, it's not a problem. So this is going to give what? So what is VP? 0. So we can write here equal to I JK of 0, 0. What is omega D?
10 million 2 seconds.
Omega.
Oh, 4.
Okay. What is the position of A with respect to P?
0.5.
0.5, 0.50. Perfect. So easy math. What will be VA? Negative 2, 2. Perfect. Okay, so what was the second rule when solving these problems? Find the velocity or the acceleration of one point from what? Two different locations. So now we can find the velocity of point A from where? From point B, no? So this would be what? BB plus omega of what this time?
Omega of B.
Of the bar AB. Call it B, A, whatever you want, but of the bar AB, no? Cross S of A with respect to B. Okay, so what do we know about VB?
Yeah, that's only in the x direction at some velocity.
Correct. Only one component, the x direction. That's important. Plus, here we're gonna have to, I'm gonna need your help a little bit with the math. We have I, J, K of 0, 0, omega B, which is unknown. But now we need to find what is the position of A with respect to B. So basic trigonometry, we have here B. This is A. So this is 1. What is the distance over here? 0.5. So this will be what? Square root of 1 minus, so 1 squared minus 0.5 squared, whatever that is. I was going to tell you to do the angle, but
3/4.
but how much is it? 3/4?
3/4.
The square root?
Distance from the two points. So
Do the distance.
root 3/2 is the distance between.
So this is square root of 2/2. I mean,
Shouldn't you add?
okay. I mean, let's see. So basic.
root
If this
5
is
over-
A, this is B.
Yeah,
What would be this?
it's root 5/2. Square root of A squared plus B squared.
What is it?
It's root 5/2.
But what is the equation? 0.866 what? So it could be square root of 3/2, something like that, no?
Yeah.
Okay.
Isn't it square root of 5/2? 1 squared plus 1/2 squared.
All right.
Square root of all that.
Square root of 3/2.
Okay, 0.866 sounds good to me. So square root of 3/2, okay? Whatever you want to do. All right, so what would be the location of A with respect to B? Negative what? Correct, but that's just for less space minus square root of 3/2, no? I agree with you. Then position of A, then what would be the Y? 0.5 and 0. Okay, so this is gonna give us the second expression for VA to be equal to what? And I'm gonna start going a bit faster, so I don't want to run out of space. So it should be equal, this should be equal to what? VB minus 0.5 omega AB now, the second term. And then this one will be negative, if you want to put this time, the 0.866. Omega AB. Okay, so now what can we do?
Solve for omega AB.
I mean, yeah, but in order to do that, what do we need to do? We need to equate 1 and 2. You have a question or at the back?
The last one you did is, you get the 0.866 based on what you did on the AB derivation?
Look at here. Okay. So we equate A and B. You see, it's all the time the same step, no? All the time the same procedure. Oh, that's fine. Ask as many questions as you want. So equating one and two, what do we have? Negative 2 will be equal to VB minus 0.5 omega AB, and 2 will be equal to negative 8.666 omega AB. Should be 0.667, but it doesn't matter, just for the example. So that's it. So what can we do over here? We can solve right away this one for omega AB. Maybe we should have kept the square root of 3/2 because this should be equal to what? Minus square root of 3/4, no? But how much would that be? Negative 0.433.
Yeah, negative 0.433.
All right, radians per second.
Two divided by negative 0.866.
Yeah. Oh, it's the other way around.
Yeah, it's the other way around.
Correct. You're correct. You're correct. So what is the inverse of this? Good point. Negative 2.3. Okay, negative 2.31. Yes, good call. Thank you. Should be the inverse of that one. Negative 2.31. Okay, now we're going to do exactly the same procedure for the accelerations, no? We don't need it. I mean, you can go and find it if you want, okay? But we don't need it. But you are correct. You can go and find it. Should not be a problem. Okay, so now if you want to, we can do what? Acceleration of A from two different locations. So let's find the acceleration of A from point P, no? We say directly. So we have acceleration of A equal acceleration of P plus alpha of the disk cross S of A with respect to P minus omega square of the disk S of A with respect to P. So we have AP plus IJK of 0, 0. What is the value of alpha of the disk? 10. And then you can use the same as before, position of A with respect to P. No, position of A with respect to P.
Yeah, so it's 1.5.
We are on the disk now. So it's 0.5, 0.5, no?
Can we go ahead and cancel,
Wait, one thing at a time.
okay,
Plus, so you want, I will do this minus omega of the disk is what? I think was 4 square of what? 0.5, 0.5. So once you become experts, what can you do over here right away?
Cancel the y component.
The A sub P is only going to cancel the Y component. Only the Y component, not the whole term. Johnny, the mistake that people do is that they cancel the whole thing. Okay, so this would give us what then? This would be equal to what? Negative 5. 5.
Wait. Oh, okay.
Okay, let's do one by one this time. Plus would be 16, negative 8, no?
Yes.
Negative 8 and 0. So this will give us the first expression for acceleration of A should be equal to negative 13, 0.
Negative 35.
Did I do a mistake here? Let's see. So the first one is the one which is going to change sign. So it's minus 5. Oh, sorry, negative 13, 5. Sorry, yes. See, I'm going too fast. No stinking. Absolutely right. Thank you. 1, 2, 3. Negative 13, 5. All right, now we're going to calculate the acceleration of point A from where? From point B, no? Let me slow down a little bit. And I'm just looking at the watch at the same time. So we want to make sure we finish. So acceleration of A from point B, but I'm going to slow down a little bit. So AB plus alpha of what?
The bar.
Of the bar, which is AB, S of A with respect to B, minus omega squared AB, S of A with respect to B. So I'm going to need your help here for sure with the calculations. So what do we know about the acceleration of B?
There's no y component.
Only X component, so no Y component. Okay, so you put it on the equation. Now the second one, that should not be the difficult one. We know it's I, JK, 0, 0, alpha B, which is what we need to find. And then we can look at before, we know the position of A with respect to B is negative square root of 3 over 2. Again, I use that one on the equation because it's shorter than the negative 0.866. And I'm looking here, 0.5 and 0. Minus.
Negative 2.31.
Yeah, so here I'm going to need your help again. Negative 2.31. Because this is omega that we calculated before, omega B. That's what we needed. And position of A with respect to B, this time if you want to put the value 0.8667, okay, or 66. But it's 66, so there's no change in now. And 0.5. So this will give acceleration of A is equal to A sub B minus 0.5 alpha AB. And can somebody give me that value here? 2.31 square times 0.8667 or 66.
4.625.
4.625. Okay. We know it's positive. Then the second equation will be 0.5 alpha AB. Sorry. Wrong. Negative 0.866 alpha AB minus 2.31 squared times 0.5,
2.668,
2.66.
668.
I don't think
Yeah.
that's right.
Again, numerical application, you are everyone responsible.
Oh, okay. That-
Okay, so final step is to do what?
Equate 3 and 4.
Equate the two equations. So, okay, let's write it down. We don't really need the first one, but let's write it down. Oh yeah, we need it because we need to find A sub B, no? Yeah, we need both of them. So AB minus 0.5 alpha AB plus 4.625. This would be equal, so let's say it will be equal to negative 13 and negative 0.866 alpha AB minus 2.66 would be equal to 5. So over here, what can you do? You can solve this one right away from 4 alpha AB.
Negative 8.855.
Okay. Negative 0.8.
855.
Okay. Okay. The procedure is correct. You check the numerical values, okay? Somebody else can double check. That would be perfect. Yeah. I mean, this problem personally, I think you should have kept more decimals. Here should have been 0.8667, no? So probably if you look at the solution, might be a bit different. So don't do that on the assignment, no? So now that we have this, we can say next from A. Now we can calculate A sub B. A sub B will be equal to negative 13 plus 0.5 alpha AB plus 4.625, which is what?
Negative 13.19.
We have my negative 13.2, it doesn't matter at this stage. Okay, so any question about the procedure, not the numerical values, because I'm not responsible. But did you follow the procedure? It's always the time, it's always the same procedure, no? We're gonna stop over here. Any question about this lecture? Okay, so we have 6 minutes.